quantum mechanics is everywhere. It's no longer just scientists in their ivory tower doing some sort of science wizardry. It is right here today. From polarized sunglasses, LCD screens, and toy lasers. But to do your first quantum experiment, you're going to need more than just a laser. You're going to need some lead sticks, or that is to say, some thin graphite sticks. And some tape. But before you get started, you should remember a couple of things about waves. First of all, waves have a wavelength, that is, a distance over which they repeat themselves. And second, when you have multiple sources of waves, they can interfere with each other and cancel out in some places. This pattern is called a diffraction pattern. So to check whether light has a wave nature, we're going to set up an experiment that lets you check both that it interferes with itself and that it has a wavelength. Start by opening your lead graphite sticks, but don't throw away the cardboard backing. We're going to use this. Start by trimming off 4 strips off of the bottom, but you're going to want to keep this hole up here. This is going to be a variation on Thomas Young's original double-slit experiment. Now, once you get your 4 strips of card cut out, you're going to want to get 4 graphite sticks out and tape them along the side of each of your strips of cardboard. Now, when you're doing this, you don't want the tape to get too thick because that's going to affect the size of the holes that we make later on. And we're going to do this to all 4. Now the reason we end up using these graphite sticks instead of, say, razor blades is not only because you're less likely to cut yourself with this, but the rounded edge of the graphite stick means that the break point of the light passing through is going to come off softly, because if you have a real sharp edge, you're going to get diffraction in both cases, and that really wouldn't be a good experiment. Now, we're going to make the one that has only 1 slit. Go ahead and put them right up so that the tape touches. What the tape is doing is it's making a very small gap here automatically for you. And then tape the top just to keep everything in place. Over here, we're going to make a double slit. Take your 2 pieces, a piece of graphite, and put it in between the first 2. Put it over the other hole. And there you have it. Single slit, double slit. Take your newly made card and first shine your laser through the single slit. Now you should be able to see on the wall that there's not much going on. Single slit is boring. Now when you do the double slit, you should see the light spread out a lot and have these light and dark patches. There it is, the double slit. That is diffraction. Get the diffraction. Get the diffraction pattern. That is quantum physics. Waves of the light are canceling each other out. They're literally destroying each other, interfering with each other, to the point where light cannot reach certain points. Look at that. Single slit, double slit, single slit, double slit. It's quantum physics. It's happening. It's right in front of you, and just for a few dollars. These things are in our world now. Turning back to Thomas Young's original experiment, we're going to do the same thing, but make it a little bit more quantitative. As you can see, I've got some rulers set up here, and I measured the distance between where the holes are, where the slits are, and where they're going to be arriving. And I also have another ruler up here that will allow me to measure the distance between the light points and the dark points. And in particular, I'm interested in the distance between 2 light points. So what you're going to do when you have your setup is make sure you know this distance here. It can be whatever you want. I found that 30 centimeters works for what I'm doing, but you can play around with it. Make sure that the measurement here is about the same height as where your hole is over here. And just go ahead and shine your laser through here, just like when you were playing around before. So if I look at about 2 fringes, so about 5.5 millimeters, and this is 30 centimeters away, and that's the second fringe, and there's one more number that we need, and that's the distance between the 2 holes, but fortunately, that distance is the width of our graphite sticks that we started out with, this nice 0.7 millimeters. So there, we have all our numbers. Let's go plug them in. 0055, 0.0007, 3, 2, and then we plug it into good old Wolfram Alpha. Oh man, did I do this wrong? That's wrong. So, as you can see, I was having a little bit of trouble getting everything right. I finally realized what I was doing is I was actually measuring the distance between the light and the dark spots for Fraunhofer diffraction, which is not what I was looking for Young's double-slit experiment. If you don't know what that is, it's when you just have one hole and the slit becomes smaller and smaller and smaller, and Derek does a really great demonstration on this, and it also produces those light and those dark bands, but in much, much more of a spread out fashion. And for the double slit experiment, those points are way closer together, and so what was actually happening is I was getting both of those effects right on top of each other, and I was only able to see one because I was taking the distance so short. So the new setup here has it a lot further from the wall, so I'll show you the details. Here I've put the laser onto a cup, just taped it down there so that it stays on all the time. I have a new double slit here. I actually switched this to 0.5 millimeter graphite because the 0.7 was a little bit big. I was able to see it eventually with the longer setup, but it's, you know, not as pretty. It's at about 130 centimeters from the wall. Now, it's really important that it's at least 100 centimeters from the wall, a meter from the wall, because anything less than that, you really can't make out the true diffraction pattern for Young's double slit experiment. You end up just seeing mush. Now you see how tightly packed those are. Those are way closer together than when I was showing the cat earlier. What we're going to do now is I'm just going to carefully take a white card and start counting those fringes. 1, 2, yeah, 6 and like 9.5. Time for calculation. First, we're going to take our first variable there and convert it to meters. So instead of the 9 millimeters, we're going to have 0.009 millimeters, and I'm going to actually put 00925. I said it was between 9.5 and 9 where it actually fell. I can't really be more sure than that, so I'm just taking the difference for starting out, acknowledging that I'll have a 0.5 millimeter error in there somewhere. And then we're going to need to multiply that by the distance between the slits, which, since I switched to the 0.5 millimeter graphite, that's the distance, is 0.5 millimeters. So when we convert that into the correct units, we get 0.0005. Now we're going to divide that by the number of fringes. That's just a straight number. It doesn't need to get converted. Then we're going to multiply that by the distance away. So I have 130 centimeters. Let's convert that to 1.34 meters and enter. That's the right number of units. That's 529 nanometers, which is orange, not red. See, that's 625 there. See that? Yep. Yep, I mean, I saw some sources that went as low as 6, but this is below that. That's why I allowed for some error. The total error could be as high as 625 nanometers, solidly red, or as low as 560 nanometers, which is just brushing up against yellow. That looks pretty red to me, but we figured it out. We figured out that this laser has a wave nature, both that it interferes with itself and that it has a specified wavelength. Right, so you see that? 650 nanometers. So I probably underestimated the wavelength. It was a little bit short because I had it a little bit oranger, but still definitely at the top end of the spectrum. But I don't have to trust the packaging anymore because I figured it out myself, and you can science it too, or figure it out yourself by visiting the blog post that details the steps that I showed you here today. But you might recall that I also talked about quantum mechanics in general at the beginning of this video, and all I really proved was that light has a wave nature. That's all Thomas Young's original experiment proved after all. This is the first of 3 videos. There's going to be 2 more that talk about how quantum mechanics manifests itself in our world today, and they'll go over some experiments that you yourself can do. And if you're curious to find out more, just click the subscribe button so you can see when the next videos come out. But in the meantime, you don't have to take my word for it because you can science it. Who's the quantum kitty? Get it. Get the diffraction.